Dear students, welcome to the next lecture of Organic Chemistry. In this lecture, we shall start our discussion on aromatic hydrocarbons. The term aromaticity or aromatic character refers to the remarkable stability exhibited by certain cyclic compounds having conjugated bonds and planar ring systems. Aromatic molecules are very stable and they do not break apart easily to react with other substances. These molecules undergo substitution reactions but are more resistant towards addition reactions. The general requirements for a compound to be aromatic are: the compound must be cyclic, and each element in the ring must have a p orbital that is perpendicular to the ring, and hence the molecule should be planar. The molecule should be conjugated and the compound must have 4n plus 2 pi electrons. That is, the compound must obey Huckel's rule of aromaticity. Aromatic compounds are generally classified into benzenoid compounds and non-benzenoid aromatic compounds. Benzene is the best example of an aromatic compound. Benzenoid compounds can be monocyclic or polycyclic depending on the number of rings. Naphthalene and anthracene are the examples of polycyclic benzenoid compounds. Non-benzenoid aromatic compounds include compounds which do not have structural similarity with benzene but show aromaticity. Examples include several stable ions such as cyclopentadienyl anion, cycloheptatrienyl cation, etc., and several heterocyclic compounds. Pyrrole, pyridine, indole, etc. are examples for non-benzenoid heterocyclic compounds. And both benzenoid and non-benzenoid aromatic compounds obey Huckel's rule of aromaticity. Now let us see the number of electrons in each system and how do they obey Huckel's rule of aromaticity. In benzene, there are 6 pi electrons and the number of rings is 1. According to Huckel's rule of aromaticity, the compound must have 4n plus 2 pi electrons, where n represents the number of rings in the compound. So if n is equal to 1, we get 4n plus 2 as 6. And the molecule benzene has 3 double bonds and each bond contributes 2 pi electrons, and thus the total number of pi electrons is 6. And thus benzene obeys Huckel's rule of aromaticity. In the case of naphthalene, there are 2 rings fused together. So n is equal to 2. If we substitute n is equal to 2 in 4n plus 2, we get the total number as 10. And naphthalene contains 5 pi bonds and correspondingly 10 pi electrons, and thus the molecule naphthalene obeys Huckel's 4n plus 2 pi electron rule. Very similar case is observed in anthracene. It has 3 rings fused together. There are 7 pi bonds and 14 pi electrons. When n is equal to 3, 4n plus 2 becomes 4 into 3, 12 plus 2, 14 pi electrons. Anthracene has 14 pi electrons, and thus the molecule obeys Huckel's rule of aromaticity. In the case of non-benzenoid aromatic compounds, if we consider pyrrole, it has 4 pi electrons, and the lone pair of electrons of nitrogen will also take part in the delocalization. 4 pi electrons from the double bond and 1 lone pair gives 6 electrons for delocalization, and pyrrole is a monocyclic ring. N is equal to 1. According to Huckel's rule, pyrrole should have 6 pi electrons for the delocalization. There are 4 pi electrons and contribution from 1 lone pair, so that the total number of electrons for delocalization is 6, and the molecule obeys Huckel's rule of aromaticity. Pyridine is a 6-membered ring with nitrogen as the heteroatom. It has 6 pi electrons, and the number of rings is 1. Hence the molecule obeys Huckel's rule of aromaticity. Indole is an example for bicyclic non-benzenoid system. It obeys Huckel's rule of aromaticity. It has 8 pi electrons, and the lone pair of electrons on the heteroatom nitrogen also contributes for the delocalization, and thus 8 pi electrons plus 1 lone pair giving 10 electrons for delocalization. The number of rings in indole is 2. So substituting 2 in 4n plus 2, we get total as 10, and indole has 10 electrons for delocalization, and hence the molecule obeys Huckel's rule of aromaticity.